sklearn, Gaussian process, kernels, pairwise kernel. Description: the pairwise kernel is a versatile kernel that allows for the construction of custom Gaussian process kernels based on a user-defined function that measures the similarity between pairs of data points. This function provides a great deal of flexibility for modeling diverse relationships between data points and capturing complex patterns. Inputs: metric, a function that takes two data points as input and returns a scalar value representing their similarity. This metric can be any function that returns a scalar value, allowing for customization based on the specific application and data characteristics. Quarks: additional keyword arguments that are passed to the metric function. This allows for further customization of the metric based on the specific requirements of a problem. Outputs: kernel function returns a kernel function that can be used in a Gaussian process model. This kernel function encapsulates the similarity information captured by the metric, allowing the Gaussian process to learn and predict based on the relationships between data points. Quarks: the same keyword arguments passed to the metric function, which are passed along to the generated kernel function for consistency. Steps: the pairwise kernel takes as input a metric function that defines the similarity between pairs of data points. This metric function can be any function that returns a scalar value. The pairwise kernel constructs a kernel function that calculates the similarity between all pairs of data points using the provided metric function. This similarity information is then used by the Gaussian process model to learn and make predictions. Metrics: the choice of metric is crucial for the performance of the pairwise kernel. Different metrics can capture different aspects of similarity between data points, leading to different kernel functions and ultimately different model predictions. Visualization plots: by visualizing the kernel function, one can gain insights into how the chosen metric captures the relationships between data points. Fine-tune parameters: the pairwise kernel itself does not have any tunable parameters. However, the choice of metric and the corresponding quarks passed to the metric function allow for fine-tuning the kernel based on the specific problem. Uncertainty methods: the pairwise kernel does not directly influence the uncertainty estimation in a Gaussian process model. Uncertainty estimation is handled by the Gaussian process model itself. Challenges and fixes: Challenge 1: choosing the appropriate metric function for a given problem can be challenging, as different metrics capture different aspects of similarity. Sample use case that resulted in challenge 1 in a problem involving image data. Using a Euclidean distance metric might not capture the similarity between images well, as it doesn't consider the spatial relationships between pixels. Fixes to challenge 1: explore different similarity metrics, such as cosine similarity or a custom metric tailored to the specific image features, which could potentially capture the relationships between images more effectively. Experiment with different metric functions and evaluate the performance of the resulting kernel in the context of the specific problem. Challenge 2: handling large datasets can be computationally expensive, as the pairwise kernel needs to calculate the similarity between all pairs of data points. Sample use case that resulted in challenge 2: processing a large dataset of images might require a significant amount of computational time for the pairwise kernel to compute the similarity between all pairs. Fixes to challenge 2: use efficient data structures and algorithms to compute the similarity between data points. Consider using approximation techniques, such as Nystrom approximation, to reduce the computational complexity of calculating the kernel matrix. Explore dimensionality reduction techniques to reduce the number of data points before applying. The pairwise kernel.